Welcome to December 29th LeetCode Challenge, populating next right pointers in each node. You're given a perfect binary tree where all leaves are on the same level and every parent has two children. The binary tree has the following definition. You have a structure of a node, you have an int value, you have a node type left pointer, you have a node type right pointer, you have a node type next pointer. Populate each next pointer to point to the next right node. If there's no next right node, the pointer shall be set to null. Initially, all next pointers are set to null. So we're given example 1 here. We're given this perfect binary tree from 1 to 7. And we want basically each node to point to, the next pointer to each node to point to null. Essentially, this is the input. If you're given the output, it would be basically 1 points to null, 2 points to 3 points to null, 4 points to 5 points to 6 points to 7 points to null, and that's basically the output. Here's a base case here. If the root is empty, return an empty list. Constraints are that the number of nodes in the tree is in between the range 0 to 10 to 12 minus 1. The number of the value of the node itself is negative 1,000 to 1,000. You may use constant extra space, only use constant extra space, as to say. The recursive approach is fine. You may assume an implicit stack does not count as extra space for this problem. So that's probably what I'm going to do, recursive approach. Specifically, recursive depth first search approach. So let's do a little bit of a theory behind why I'm doing that. So recursive depth first search. The current node of the tree is responsible for linking the nodes of the left branch and the right branch together. So if we were to do a depth first search, we can eliminate the root node and therefore find the central axis of all the sub branches below it. Okay, that's kind of a formal way of putting it, but so let's say we could, most of them are on the, if we're concerned with, for instance, level 1, right, where the one node is located, we just assign that to 0, and we assign that to null. The next thing we're actually concerned about is the only 2 and 3, and we want that to be on the same depth, right? And that's the only way we can manipulate it together. So that's why depth first search is important. And then we can just recursively split the tree into smaller branches, and then point the left node to the right node. And that's our approach. So the first thing we want to do is get rid of this base case right here if the tree is empty. So if not root, return root. Let's do that. So if root.left, so if the root of the tree has a left node, we're going to do this following. We're going to assign a left variable and a right variable. And these are just kind of current pointers we're going to work with in order to assign left to right. And we're going to assign that currently to root.left and root.right. Alright. Pretty much just variable assignment at this point. The next thing we're going to do is, on the same if statement, we're going to do a recursive call, connect, left, self.connect right. So this is the initial, we're starting our recursive call. So essentially, if we have a left node, we do the variable assignments, and then we do a recursive call, then that's going to go through it again. However, this is the meat of what we're trying to do, so we're trying to assign the left pointer to the right pointer. So while we have a left node, we are going to say that left.next will be pointed to right. Right? While 2 exists, while this node right here exists, pointed to 3. And it's a while loop, so it's going to keep on pointing to the left, so it's going to be pointing to the right while this case is true. And it is going to be true because we are reassigning left and right afterwards, and that's going to be left dot right, and then it's going to be right dot left. It's a bit it's a bit of a messy nomenclature here, but we're basically saying let's reassign the values of the left node of the right pointer right here to be the new left, and the right pointer here of the new right pointer to be the next right. So basically, we want to basically point 6 to 7 to null, which is already done. And then if we recursively do this, we can point 4 to 5 to 6 to 7 and then to null. And essentially, we can return root. Not there. There. All right. There you go. That seems to be working. Ta-da! There you go. So time complexity would be big O of n, because we do a while loop for each of the node. We're doing a recursive approach, but we're assuming that the implicit stack does not count towards extra space of this problem, so the only thing we need to count is the while loop for each node we iterate through. Space complexity is constant space. Alright, that's it, guys. Have yourself a great day using recursive depth first search approach.